So, last lecture we saw that the orthogonal group, the set of elements in that can be written in the form of, I guess, special orthogonal matrices. So, let us call them R and P dot R, where R was a SOD matrix. Okay, so, right now you can think of this as the set of OD matrices. Okay, and of course, the composition rule is the standard thing. Okay. So, it is not hard to see that if you multiply 2 of these elements, you will end up with an element which is out here. So, I will not prove those things, but this is something we saw last time. We also saw that we can specify the action under P, which is parity, P for parity. It is just P is something which just square to identity, and of course, it is orthogonal matrix, and that P was -1. So, we saw, for instance, if you take vectors, SOD vectors, you classify them into 2 kinds, polar and axial, depending on how they transform under P. Okay. So, quite often we will see such discrete groups. By discrete groups, I mean a group which has a finite number of elements. We will be discussing it maybe later in today's lecture, or maybe in the next lecture. So, what you can see is that in principle this is the symmetry of our system, but we were only looking at the SOD part of it, but really it is there. And hopefully you check that the electro E field is a polar vector field, while B is axial. This is a consistent assignment. If you write out Maxwell's equations, this is what you would get consistently. Okay. So, later we will see that when there are 4 vectors, there will be more transformations like P. Okay. We could include something like time reversal, how things transform under that. So, you will have to specify various things such as what I have given out here. Okay. So, now what we will do in the next lecture, in this rest of the lecture, is to look at 2 kinds of generalizations. Okay, of OD or SOD, as the case may be. First one will lead us to what we will call the analog of the Lorentz group. That is what we will do next, but the other generalization will lead you to what I will call just matrix groups. Okay. So, in particular what I have in mind is what I call the unitary and symplectic. Okay. So, let us look at what the generalization which leads you to the Lorentz group. Okay. So, recall that we defined SOD by or OD by looking at vectors, taking some vector V1, V2, Vd, and defining it to be the set of linear transformations which preserved the length of this vector, and the length, or the, let us use the notation V for this short form. So, mod of V square was sum over I. Okay. So, what we will do now, and this norm has special properties. For instance, if the only vector which has 0 norm is the 0 vector, okay, that follows because this is a sum of squares, and the only way this object can be 0 is if every term is 0. Okay. Of course, implicit in my thing is that these are all real numbers, but even if they are complex, okay, right now these are real numbers. Okay, so what we will, the generalization which will give us a Lorentz group is the following. Consider, so let me be very specific here, and let us consider a 4 vector I will use the same notation, but you will we already saw examples of 4 vectors, and I will define a norm which is slightly different from so this is the norm which I will attach to a 4 vector. So you can see that here it was a sum of 4 positive. So even if you take D to be 4, it would look like in terms of vectors it would like, okay, I can write my vectors going 1 2 3 4 or 0 1 2 3, but what we have out here is a different norm, okay, which has minus signs out here. Okay. So so you can see that already this norm square is not positive definite. Okay. In particular, if you said that the norm of some vector 4 vector is 0, it does not follow that it is a 0 vector. 0 vector of course satisfies that, but you could have situations where V0 square is cancels precisely cancels this quantity. Okay. So, but from the viewpoint of defining, so we will define the group O 1 comma 3 to be the set of linear transformations that let us give this norm a name, let us call it a Lorenzian norm. As opposed to an Euclidean norm. Okay. So what we have is a Lorenzian norm, and this 1 and 3 tells you that there are 1 pluses and 3 minuses, but if a little bit of thought will show you that actually I could have written 1 minus and 3 pluses, that will not really change the story. Okay, so I can redefine my norm with a overall minus sign, because now that we are giving up positivity of norm, there is no special thing about this being thing, but in this course we will always work with this kind of a norm, and that preserve the Lorenzian norm of 4 vectors. Okay, and let us introduce the Minkowski metric. So in principle I could have called this the Minkowski norm also, the Minkowski metric. Okay. In keeping with our earlier things, I noticed that I have defined this to have 2 lower indices. Okay. This is the Greek symbol eta, so it is eta mu nu. So it is a diagonal mate. If you think of it as a 3 by 4 by 4 matrix, it has plus 1 in the 0 0 entry and minus 1 in the 1 1 2 2 and 3 3 entries. So, the advantage of this is that I will rewrite the norm now in the following way. Okay. At this point, and again the reason I put this with two lower indices is that I want to satisfy the rule which I have introduced long ago, which says that we can only a repeated index should one lower and one upper should be summed over. So, if you look here, I am very careful, I am writing out the summation out here, because I am implicitly violating that. Okay, that is why I write this summation out here, but here I am not violating anything like this. Again, you can see that you can think of this entry as a column vector and this as a row vector, and this multiplication again will give you exactly this. Okay. So, this is a very concise way. Okay. So, now let us go ahead and write out the linear transformations which preserve that metric. So, we will see that it is no longer O transpose O equal to identity, but it will be a variation thereof. So, let us consider, so some linear transformation would just tell you that it has to be of this form. Okay. And now what we want is so we look for linear transformations which preserve this norm. Okay. So, let us go ahead and now I will write it symbolically. This thing I can write as V transpose dot eta dot V. This is the same thing as this is the same as this, but now I have hidden all the index structure, but you more or less you know what it is, because you know eta as I defined right now, it is a lower index. Okay. So, let us look at start from here and see what okay. And so, this again I will let me write it by hiding the indices, it is V prime equal to O dot V. Okay. So, here I need to so this would be equal to O dot V transpose dot eta dot O dot V. Okay. So, now under transpose these things exchange, so you get O, this is equal to V transpose times O transpose and the question is this equal to V square? So, let us put this question mark. Okay. So, you can see that so this has to hold for any V. Okay. So, you can see that that can happen only if O transpose eta O is equal to eta. So, now we have that definition is made much more concrete, and we see that. So, the condition is, so we obtain O transpose dot eta O is equal to O equal to eta. Okay. So, now it is a good thing to go back and put back the indices, and we should remember O is such that O, the first row index is an upper index, while the column index is a lower index, but for O transpose these two will get rows and columns get exchanged, but you do not bring this down. Okay. So, let us write out. So, O transpose will be something which has its first index as lower and the second index as higher, upper, and then eta of course has two lower indices. So, let us call it nu and sigma, and there should be some free index. So, let us call it rho. Okay. So, that is I am just putting in indices to these various things. Okay. See, I have taken care that I am not violating any of the rules which I mentioned, and so now nu index is repeated. So, you can it is a dummy index, you can forget it, sigma index is this, only the free indices are mu and rho. You may worry, should I write mu rho or rho mu, but coming back to the original definition, that is a symmetric matrix. Okay. So, what we will do is all norms which we will look at will be symmetric, we do not violate that bit. Okay. So, this is the definition of an orthogonal matrix. So, now again it looks very complicated, and but we can still ask a few statements about this. What about determinant of O? So, like before, if you take the determinant of the left hand side, it is equal to determinant of O transpose times determinant of eta times determinant of O equal to determinant of O eta. The determinant of eta is non-degenerate, it is non-zero, it is equal to -1 in my convention. So, that is -1's cancel away, and you can see that again the condition is determinant of O is equal to, rather square is equal to 1, the same as before. Okay. So, this implies okay. So, obviously we can define SOD is the subset, rather SO1 comma 3 is a subset of O1 comma 3 matrices that have determinant 1. Okay. So, are there any questions with regard to this? It is very easy to go back and check that the composition of two such orthogonal matrices, these are still called orthogonal. Okay. Orthogonal matrices satisfies the group properties. In particular, the product of two such things will give you another. So, go home and check the following thing, take O1 and O2, assume both O1 and O2 satisfy this condition, and check that O1 dot O2 and O2 dot O1 both satisfy the same condition. Okay. It is not very hard, it is very simple, but it is useful to check these things, keep the axioms next to yourself and check each one of these things and work them out. Okay. So, now the interesting thing is what are the matrices not in SO1 comma 3. Okay. Actually, before we answer this question, let us ask what are the kind of matrices which would be in SO1 comma 3. Okay. So, let us denote as a SO3 matrix. Okay. So, now I have a question for you. So, these would be in this case, because these are linear transformations acting on a vector of length 4. So, this would be 4 by 4 matrices. So, R here is just a normal rotation, it acts on 3 vectors. Now the question is, can we convert this, given such a matrix, can we actually rewrite it as a SO 1,3 matrix? Okay. So the question is, how would one do it? Anybody? I want to write a 4 by 4 matrix. Okay. So under rotations, so let's go back and look at what happens under rotation. So we look at, it's simpler to just work out, take the example of the position 4 vector and ask how it transforms. So what we know is that, let me erase this first, and under such a transformation x0 prime goes to x0 and xi prime goes to ri j xj. Just remember our convention that the Roman indices run 1 2 3, they stop there. Okay. So now you can see that, so this is a 3 by 3 matrix, but we need to combine these things into a 4 vector, and it is kind of very easy to see how this happens. So we can write, maybe let us put a hat to indicate this, it is 1 r and there are zeros. Okay. In principle there should be 3 zeros here, 3 zeros here, I do not indicate the 0 elements. This is a 4 by 4 matrix. Okay. You can go back and I claim that this is a r hat satisfies this condition. Okay. So exercises, you might think that the problem would be because of this minus sign, but actually it will not be a problem. Okay. Because there will be a minus sign on both sides which cancels away. So really the basic property which you have for r, which by the way you can write as r dot delta dot r equal to r. Okay. So it is useful to remember that. It is not a rotation. I would not call it a rotation. If it involves x0, I would call it a boost if there is something which involves that. So obviously this is that is why it is an SO3 rotation matrix. Okay. But to show you that your normal rotation matrices are indeed examples of this thing. This is something which we already saw when we worked out the invariances. It was by inspection, there was nothing to check. Okay. So the only question is, what about Lorentz boosts? Okay. So let us simplify things. Yes.
If you look at delta being the metric for the Euclidean space and eta for the Kawski space, would you say that any equation of the form of matrix transpose metric matrix, that is the definition of rotation
of orthogonal matrices? So the general statement is that let replace eta by any symmetric matrix. Okay. And then you can define the orthogonal group to be of this form, but you can always bring eta to be if you are given a symmetric matrix, you can always make it look diagonal, and you can even use some scalings and you can bring it down to a simple form, and all that will matter is actually the number of things which have plus and minus signs. So we have, I wrote 1 comma 3 which has 1 plus sign and 3 minus signs. In principle I can define something called the O p comma q, which is p plus signs and q minus signs.
So what is the restriction on if we are to construct a metric?
It has to be symmetric.
Any symmetric tensor can be always reduced into O p comma q.
That is right. Okay. So if you replace this by some antisymmetric matrix, you will get symplectic matrices. Okay. So that was the generalizations which I was just going to talk about, but I just wanted to complete the definitions of what we would mean by the Lorentz group in an abstract setting. So this is it, and so but we still need to work out Lorentz boosts. So an example of a Lorentz boost okay. So I what I will do now is to write it in a slightly different form, and so let's look at a boost. So let's say a boost in the x direction or x1 direction. Okay. So in other words, what I have in mind is x0 prime should be equal to O00 x0 plus O11 x1, and it does nothing to x2 and x3, and x1 prime is equal to O10 x0 plus O11 x1, and of course x2 prime equal to x2, x3 prime equal to x3. Okay. So this is the transformation which we would like to plug into this, and we would like to check. Okay. So so one thing you can see here is that this, whatever you get, this should be this will be an equation which is quadratic in the O's. Okay. So and it's important, another important point here is that eta has a minus sign. So from the subspace which we have, there is really nothing to check in this in the 2-3 space. So it reduces the problem to a 2 by 2 problem, which I will not work out. I will write out the solution for you. Okay. What you will find is that O00 equal to O11 should be equal to O10 equal to O01 should be equal to sine hyperbolic phi. Okay. So this is very similar to rotation matrices, except that what is happening out here is that the sine and cosine functions get replaced by hyperbolic functions, and the hyperbolic functions have crucially have a minus sign in this simple identity. Okay. So this minus sign has its origin in the minus sign in out here. Okay. So you can see that this is the unique solution, but unlike when it was a trigonometric function, theta was identified with theta plus 2 pi. This has no periodicity. Phi can take values from minus infinity to plus infinity. Okay. So it is also an exercise to check that what I had written the same boost, that you could rewrite things in terms of some gammas and stuff like that. You will check, you can check that gamma is equal to cos phi and beta equal to tan hyperbolic phi. This quantity phi has a name, it is called rapidity. Okay. So what I will do now is to write this particular matrix out in 4 by 4 form, so that you can see for yourself how it looks. So let me call this matrix, it is a boost in the x direction with rapidity phi. Okay, I am not writing out the zeros again. So these are 1 1 out here, these would be zeros here, there would be zeros out here. Okay. So, this is what you get, there is a boost in this thing, but there is a nice thing which happens if you compose two boosts along the same direction. Let us do 2 first, 2 second, does not matter, you can show it is equivalent to a boost in with okay. So, what this tells you is that at least life is not so bad. I mean, if you take two boosts in the same direction and compose it, it works like exactly like angles added, except this what is adding is rapidity. Okay. But now comes the neat stuff, beta was V upon C. So, you have an addition rule which you get, which is so in the non relativistic setting we know that if you take two boosts in the same direction, then they add, the velocities add. Okay. But what this is telling you is that this is not true. What adds is the phi 1 of phi 2, phi 1 and phi 2, which is rapidity. So, the velocity, so V prime, so let us say that this is related to, so V1 V2 is equal to tan hyperbolic phi 2 and V1 equal to tan hyperbolic phi 1. Okay, I should divide by C, but I will set C equal to 1 because it is, I mean you can always put it back. Okay. So, now what this tells you is that the addition rule will tell you that V prime would be tan hyperbolic after you compose them together. So, let us call this B okay. Now, hopefully you know your tan hyperbolic addition formula, it is almost the same as the tan thing with some minus signs here and there. Okay. So, what is it? I do not, let me write it out, I will fix the sign, we can always fix it, I think. Is this correct? Okay. Plus on one and minus on the. Okay. Now comes the so already you can see out here that V2 equal to tan hyperbolic of phi 2. It you can see the following thing, the tan hyperbolic function is bounded from above and below by plus 1 and minus 1, and so this is, so it tells you that V2 equal to actually let me put the C's back, then you will see this. Okay. So, you can see that there is an upper bound on speeds which is C. Okay. This is an algebraic way of seeing it as an implication of various things, and so you also can see another thing, you may think, fine, what happens if I have two things which come with velocity c by 2 c by 2 facing each other. So, it should add up and you should get something, you would think naively it should add up to give you C, or then you can check that whatever you do out here, that will not work. I mean in principle you can see if one of them, one of the tan hyperbolics becomes 1, then this should also become 1. So, now that tells me that there is a sign error, this should also be plus then. This, I was using that to check things. Okay. So, but this is standard, and so now you can see that if tan phi 1 to phi 2 becomes 1, this cancels away and this also becomes 1 or C, and now that I have put back the. Okay. So, this is sort of an algebraic way of seeing these things. Okay. But the meat comes because this is the invariance of Maxwell's equations, which has a scale, which has a velocity, natural velocity built into it. So, one of the exercises which I have given you in your next assignment is to work out a boost matrix in some arbitrary direction. Okay, not x1, not x2, not x3, each of these things we know how to write. Okay. You can do that, and one more thing you can see is that the idea of a Lorentz boost reducing to a Galilean boost is also easy to see out here. It is just a limit when the velocities are small, v over c is very small, magnitude of that is small compared to 1, then we can approximate tan hyperbolic function by its argument. Okay. So, v2 would become for small velocities, v2 is actually c times phi 2. So, what you can see is that what we at low velocities, which we look at things, what we perceived as addition of velocities actually comes, you can trace its origin to addition of rapidities. Okay. So, you have to work out this exercise, it can be a little bit painful, but there is actually a very simple way of doing it. Okay. So, which I will not tell you now, I want you to sweat over it, and next week when we will discuss it sometime, I will work it out. Okay. So, yeah, so now I have more or less I have shown you that at least this group which we started writing out has some semblance of what we wrote out as Lorentz transformations, Lorentz boosts. Okay. So, so now, but there are still what are the matrices which are not in SO13? Let us look at that. So, we need matrices. So, what we are doing is we are looking for matrices which transform like O transpose O equal to eta, and we already knew one determinant -1 matrix. What was that? Parity, but that was written as a 3 by 3 matrix. So, we need to upgrade it to a 4 by 4 matrix, and how would we write that? So, we had chosen, let me remind you, the P 3 by 3 matrix was okay. I did not choose it to be all -1s because I was writing formulae for arbitrary dimensions, and so invert in even dimensions we saw that if you invert all of them, then you get something else. Okay. So, what would be P hat? Under parity, what happens to time? You just ask that question, nothing. So, nothing is put by putting the same way like that. Okay. And obviously, the determinant of this is -1. Okay. So, this is the first example. The second example is what we will call T, which is time reversal. Okay. And T would be reverse inverses. So, again its determinant is -1. Okay. So, I leave it as an exercise for you to think if there are any more. Okay. Okay. So, now in the next 10 minutes or so, what I will do is I will discuss the other generalizations. So, before I do that, do you have any questions with regard to what I have done so far? So, now I have given you a proper definition of what we mean by the Lorentz group. Okay. And I have given you some evidence as to how it relates to what we did a few lectures ago, couple of lectures ago. Okay. So, now the generalizations, already somebody asked a question. So, okay. So, what we saw here was we replaced the Kronecker delta with eta, but in principle I can just replace it with any symmetric matrix, real matrix, okay, and that will give you a norm, but this is just a claim which I will not. You can reduce such a matrix by similarity transformations and scalings to a diagonal form. You go around play with this, okay, with say certain number of minus ones, let us say p of them and plus ones. Okay. Such a group we will call this. So, any O transpose. So, let us call this also eta, but eta pq to keep this called the signature. Okay. O transpose okay. So, this will give you the group O P comma Q. Thanks. So, it is just if you give me any matrix, it is like a change of basis. So, it is just any matrix M, determinant of S of course should be non-zero, that is the only thing. So, M goes to, I will call such a thing a similarity transformation. So, if you think in terms of vectors as elements of linear vector spaces, a similarity transformation is nothing but a change of basis. Okay. So, the second generalization is the following. So far we assume that V1 to Vd belong to reals, but suppose each of these elements belong to complex numbers, okay. And let us have a norm which is real. So, I just define to be the following mod okay, and define I do not put minus signs here. So, you define, you go ahead and look for linear transformations which preserve this norm, and you get a condition which I will just write out for you, u dagger dot u equal to identity, okay, because what we have here is V1 star V1, okay. So, u dagger is u transpose star, and u's need not have real entries anymore, they can have complex entries. So, these are called unitary matrices. So, this will give you another group called ud, okay. And I must tell you, if you there is a difference between the maths and physics books. Physics books will use dagger, but maths books will use star and never ever tell you that there is a transposition, but it is there, okay. It is just a different convention. In physics we use a different symbol for complex conjugation in this thing, and for them it is not. So, it depends. If you look at a math book, kindly accept star to be equal to dagger. In a physics book it is not, okay. So, this is just important notation. So, this is the second generalization, and there is something fun out here. So, any complex number can be written as set sum of two real numbers with an I put in there. So, if you look at that thing, this each of these terms will be the sums of the squares of the real part and the imaginary part. So, you could rewrite this thing as a 2D dimensional vector, okay, but there is some extra structure out here. So, what you find is exercise, okay, show that ud is a subgroup of SO2D, okay. There are elements of SO2D which are not UD, okay. So, we again will one uses set theoretic notation. So, what this means is that as a set this is a subset, but it is also a group, it preserves group. So, whatever is inside this thing, so the same symbol is used, there is no need to invent new symbols because something is a group, okay. So, whenever, I mean, this is standard in math, that whenever you have a set with some extra properties, you expect I mean and two sets with similar properties, when you say subset it means it preserves that property. In this case it is group composition. Okay. So, this is a fun exercise. The last one is, by the way, there is similar generalizations like putting some minus signs, certain number of minus signs, etc. So, you can define u p comma q. Okay. Now, the third one is instead of looking at norms, okay. So, you look at antisymmetric objects. No, I mean I will call it a norm. Okay. So, the key is that instead of norm I will just call it an inner product. Okay. Suppose I have, let us call this W and V, two such guys. I will, and omega, let omega is antisymmetric. Okay. Then I can define some sort of an inner product okay. If I exchange these two it is antisymmetric. So, clearly if I take the same two guys I get 0. Okay. This is antisymmetric, and let us assume this is non degenerate. That means determinant of omega is not equal to 0. Okay. For antisymmetric matrices one can prove that if you have a odd dimensional matrix it necessarily has one 0 eigenvalue. Okay. So, this implies that D must be even. Okay. So, what I started out with looked like D could be odd. If I put in a non degeneracy condition you can okay, you will get a condition, and again we can look at the set of linear transformations that preserve such an antisymmetric object, and it will be a similar formula. So, I will just call it, okay, let me use the symbol S. It is the same story as before. Okay. Such again you can prove the set of such S, the set of one obtains a group okay. So, let us go ahead and say let us make D even. So, let us write D equal to 2n, and it is called the symplectic group SP 2n. Okay. So, naively again you would think determinant of S should be, if you take if you go ahead and take a determinant of this expression you would get determinant of S times determinant of omega times determinant of S equal to determinant of omega, and you would decide determinant of S whole square equal to 1. So, again you would think the determinant of S should be plus or minus 1. It turns out that proof is not so simple, it is not trivial, somewhat tedious. Okay. There are different proofs and it is a hard exercise, you have to play with it and use certain definitions. You can prove that actually this is strong enough to actually imply that determinant of S equal to 1. Okay. So, there is no minus 1 in this thing. Now, this looks like an obscure group, but actually we have all seen this thing. You take PQ, consider the following set of transformations. Okay. So, this is when d equal to 2, you ask the conditions under which the Poisson bracket p prime cube of p prime, this is a canonical transformation. Okay. You can show that this is exactly this, and where omega would be the matrix 0 1 minus 1 0, has to be that. Okay. So, these are actually what I call, so we have seen 3 examples, we have the orthogonal, we have the unitary and the symplectic. Okay. So, these are actually infinite families of groups which we have seen. For every such even integer you get a symplectic group, for every positive any real number you get orthogonal and unitary matrices. So, you have a whole infinite class of groups, and the neat stuff is that this covers almost just about almost all of a certain family of groups called Lie groups. Okay. And we will see aspects of this during this course, and but right now I think this is all I want to say about these matrix groups, what I call matrix groups, and we will move on into the next lecture where we will do finite groups, because we can be a little bit more explicit about certain things, and I can introduce certain more concepts which you can actually work out for yourself. Okay. So, that we do in the next lecture.